Dear student, as we have already seen that how the interference pattern takes place, now in that way we have also seen that if the sources are incoherent, then we will see that the total intensity that we get on the screen, that will be simply addition of two intensities. That experiment can be explained that if we use two sodium lamps illuminating two pinholes, we will not observe any interference fringes. Suppose I have here two pinholes over there, one pinhole at this point and one pinhole at this point. Here there is a separation. Now if this is the screen, if this is screen and I have two pinholes or sources, that is S1 and S2 in this manner. Suppose I illuminating them with the help of sodium lamp. So suppose I have sodium lamp. Suppose I have sodium lamp over here. So I can explain it with yellow color as sodium belongs to yellow color light. So I have suppose sodium lamp over here and it used to illuminate these two pinholes. Then on the screen we will not observe any interference fringes. This is clear because of the fact that the light wave emitted from an ordinary sources undergoes abrupt phase differences. We can say that many phase changes are there in just a time order of 10 to the power minus 10 second. So just 10 to the power minus 10 second, or we can say that 1 angstrom time period, they are undergo so many phase changes. Now thus the light waves coming out from two independent sources of light will not have any fixed phase relationship and would be incoherent. And when this happens, as discussed, we have previously discussed about these, the intensities on the screen will just add up. But how to get a coherent source? So for that, a scientist named Thomas Young used a good technique to log the phase of two waves emanating from S1 and S2. For that, what he did, we can explain that he made a new arrangement of light source in which he applied some particular arrangement through which we can explain it over here. Now what he made in this experiment, in his experiment he made a new type of arrangement that I am showing over here, with the help of which he put two sources in a such manner, like here I am showing, you will be able to see it here. Here he arranged two sources by making two pinholes on a opaque sheet, and he used one sheet for particular one main source. So here S is main source and these S1 and S2 are secondary sources. Now on the other hand, on the screen we can see over here if we go with the experiment, we find that the interference pattern that is observed on the screen with these horizontal lines, and it is very clear that we found on the screen as narrated over here. At any particular point of the screen we can have interference pattern that we observe. So what is that arrangement that he made, or he used this type of two sources? So we can say that he made two pinholes S1 and S2 very close to each other on an opaque screen. These were illuminated by another pinhole that was in turn light by a bright source. Light waves spread out from S and fall on both S1 and S2. Here S1 and S2 then behave like two coherent sources, because light waves coming out from S1 and S2 are derived from same original source, and any abrupt phase change in S will manifest in exactly similar phase changes in the light coming out from S1 and S2, and thus we can say that the two sources S1 and S2 will be locked in a phase. Now they will be coherent and the two vibrating needles as we have observed in the water ripple tank. Now if we consider them, that is S1 and S2 on another screen, that means on another view, we can draw that S1 and S2 like two sources. The screen is already there, but now this is intermediate part. This is point O on the screen as shown in the figure above. Now we see any point P of the screen. We found that the interference pattern is observed. So this is the distance on the screen, this is distance from the screen, and these are the distance between two sources or two slits. So now this was the experimental arrangement made by Young, and how the result are derived by him that we will see now. So we can have a simple calculation on base of that. We can see that the spherical waves emanating from S1 and S2 will produce interference fringes on the screen GG dash. Here we can see that this is the screen GG dash are shown. So here this GG dash is the screen. The position of maximum and minimum intensities can be calculated by using the analysis that we have discussed in earlier section. So for an arbitrary point P on the line GG dash, that is to correspond to a maximum, we have the condition for the maximum that S2P minus S1P must be equals to n lambda, where n is equals to 0, 1, 2, etc. So this is our equation 1 that we have already discussed earlier. This is called the phase difference. Now on the basis of, if we apply we have already considered that these S1 and S2 are made very near to each other, and now if we go with the condition that is S2P minus S1P whole square, that can be considered over here with the using Pythagoras theorem, we can apply that S1P and S2P becomes 2 S1P and S2P becomes hypotenuse of 2 arrangement. Here we arrange everything with respect to this point O. If we go with the condition, we can have the arrangement now that can be resultant into the term that is d square plus x plus d by 2 whole square minus d square plus x minus d by 2 whole square. So if we simplify this term, the result turns out to be very clear, that is 2xd. Now here we know that S1 S2 is considered as a small distance d, and that OP part is considered over here as a x. Now therefore we can say that S2P minus S1P whole square is equals to 2xd. Now on the basis of that, if we separate this equation with the help, we can have therefore S2P minus S1P into S2P plus S1P is equals to 2xd. Now S2P minus S1P, if we make it a subject, 2xd over S2P plus S1P. Now therefore we can say that is if S1P is almost equals to S2P, or we can say that if they are very near to each other, then we can say that S1P plus S2P is considered as a D plus D, that is 2D. If we consider this is the consideration on the basis of our assumption, then we can replace this equation, that is S2P minus S1P is equals to that is 2xd over 2d. Now this is the condition for that. If we use now we know that S2P minus S1P is equals to n lambda, that we have already considered. So therefore that n lambda is equals to xd over d, and therefore if we make x as a subject, that is for any number xn, we can have that is n lambda d over d. So this is the condition for the interference pattern that we obtain for the maximum light, where n can be considered as n is equals to 0 plus or minus 1 plus or minus 2, etc. This can be considered as our one of the equation, that we can consider it as a equation. If we have not given any equation, then we can say that this is our equation number 1 for the bright light in the interference pattern. Similarly, for dark fringes or dark light, we can have x n is equals to n plus 1 by 2 lambda d over d, where also the n belongs to 0, plus or minus 1, and so on. So these two are the equation for that maximum and minimum light intensities that we obtain on the screen. And here we can simply explain that if we use them for our screen, then we can have that dark and light fringes. So the dark and bright bands appear on the screen as shown in a previous figure, or similarly now how they look, that we will show you. That here, this is suppose the screen, then on this screen we can have some dark and bright fringes, so that can be obtained like band. Here we can apply that band in this manner. So here black part you can say that is dark fringes, and this white part considered as a bright fringes. So ultimately that would be the fringe pattern. Here we can say this portion as that equation number 1 and 2 show that dark and bright fringes are equally spaced, and the distance between two consecutive bright fringes or dark fringes are given by. So now suppose we want to produce the difference, that is also called fringe width, that is given by B is equals to, consecutive means two sequential part, so that will be obtained as lambda d over d. So this is called, that is fringe width. So equation of fringe width is given by equation number 3. So that equation number 3 belongs to fringe width, and that is represented over here. We can use this equation for that. Here the central point O on the screen above, here we can see on the screen above here, this is the central point O. So the central point O will be bright because S1O and S2O, and they are equal, and it will correspond to n equals to 0. If we consider the line perpendicular to the plane of paper and passing through O, then all points on this line will be equidistant from S1 and S2, and we will have bright central fringe, which is straight line that we have shown in the figure below. Now in order to determine the shape of the interference pattern on the screen, we note that a particular fringe would correspond to the locus of points with a constant value of S2P minus S1P. Whenever this constant is an integral multiple of lambda, the fringe will be bright, and whenever it is an odd integral multiple of lambda by 2, it will be dark fringe. Now the locus of point P lying on xy plane such that S2P minus S1P is a constant and is a hyperbola. So the fringe pattern will strictly be hyperbola. However, if the distance if the distance capital D is very large compared to the fringe width, then the fringes will be very nearly straight lines, and we can show it as shown in the bigger way, that is in the figure below. Now we should mention here that the fringes are straight lines although S1 and S2 are point sources. If we had slits instead of the point sources, then each pair of points would have produced straight line fringes and resulting in a straight line fringes width, that is increased intensities. So that is the experimental work of Young. Here it is also observed that the intensities of this light can be explained on the basis of intensity part. If we draw them here in the pattern, if we follow that above pattern, we can have the maximum intensities at a white portion, and then we have zero intensity, then again we have maximum intensity as white point, then we have 0, then maximum at white, then 0, maximum intensity as white, then 0, and at that level we can also have another way that correspond so if we make corresponding point with respect to just above figure, we can have the relation that we can show over here with the point of intersection that is shown over here, that can be explained. So here we find the maximum intensity for point here, then again we have maximum intensities at point, then again we have maximum intensities, then again we have maximum intensities, then again we have maximum intensities, and then we have again maximum intensities. So this is in the term of that Young's experiment. Just shifted the position of original source slit. That means if we have taken here, we have taken the source of hole small s on the perpendicular bisector of two slits, which is shown as line SO. So here in the previous figure that we have shown this part as this main portion of the source. Here we can say that this is main source and it makes SO line, which is on the bisector or perpendicular line of the slit. So if we go with this condition, we draw, suppose that S is a main source, here S1 and S2 are two different sources. If this is the screen, then we can simply consider two different things. That suppose we consider one point Q over here, we consider Q point over here. So we can say that what happens if the source S is slightly away from the perpendicular bisector. Consider that source is moved to some new point S dash. Suppose we shift this source at new point, that is S dash. So, and suppose that capital Q is the midpoint of S1 and S2. So this capital Q is the midpoint of S1 and S2. If the angle S dash QS. So here I say that S dash QS is suppose phi, then the central bright fringe occur at an angle minus phi. So here obviously the central fringe will be at some angle that is minus phi on the other side. So here, which was initially presented like this, we can say that now the bright fringe would occur at this point. This can be considered as minus phi as an angle. On the other side, now thus if the source S is on the perpendicular bisector, then the central fringes occur at point O, also on the perpendicular bisector. If S is shifted by an angle phi to point S dash, then central fringe appears at point O dash and angle phi minus. So here this is actual O point. Now suppose this is O dash. So we can say that this would be minus phi angle, which means that it is shifted by same angle on the other side by the bisector. This also means that the source S dash, the midpoint Q and point Q dash, and point O dash on the central fringe are in the straight line. So that S dash, Q and O dash are all in the same line. So this is also one of the observation we can show over here. So after all this, we can express that the statement by a Dennis Geber. Now here he stated that the wave nature of light was demonstrated convincingly for the first time in 1801 by Thomas Young by a wonderfully simple experiment. He let a ray of sunlight into a dark room, placed a dark screen in front of it, pierced with two small pinholes, and beyond this, at some distance, a white screen. He then saw two darkish lines at both sides of a bright line, which give him sufficient encouragement to repeat this experiment, this time with spirit flame as light source, with a little salt in it to produce the bright yellow sodium light. This time he saw a number of dark lines regularly spaced. The first clear proof that light added to light can produce darkness. This phenomena is called interference. Thomas Young had experimented it, and it was expected it because he believed in wave theory of light. So this is from Young's experiment of interference.